Hi, it's time for another math easy solution. I'm trying to discuss further into trigonometric substitution for integrals, and now go over example 3, which is basically this one here, which states to solve this integral, which is 1 divided by x squared divided by square root x squared plus 4 dx. Now in solving this seems pretty complicated, but if you recall from my earlier video, that when you have something like this where inside the integral a square root of x squared plus 4, in this case this is the same way as writing, well, 2 squared plus x squared. And in my earlier video on trigonometric substitutions, yeah, I showed that if you have something like this, then you could apply the trig substitution. Yeah, basically let x equals, and in this case 2, which is, this is going to be the number we put, and then tan of theta here, tan theta. So we're going to switch the variable from x to theta, and in this case what we're going to get is, well, dx is going to equal 2, then the derivative of tan, that's just going to be secant squared theta, and then always include the d theta at the end. So now what this becomes is basically this x squared plus 4, this equals 2 when we add this variable. That's just going to be, this is going to be 2 squared times by this tan theta squared plus now 4, or which is just going to be, well, 2 squared. And then we take the 2's out, so we get 2 squared. This just becomes, well, these add up, is just going to be 1 plus tan squared theta. And now, like I showed in my earlier video on trig identities, this right here is equal to secant squared theta, and you can see the proof for this also in the video links below. So now that we have all that, we could greatly simplify this. So then 2 squared, square root of that is just going to be 2. And now this will just be, well, square root secant squared theta, and this equals to 2. Now we have an absolute value of secant theta right here. And the reason it's absolute value is because inside this square root, it has to be positive, but secant can be negative, so we make an absolute value of it. And to get rid of this absolute value, well, if we just look at, if we look at the graph right here, if this is going to be, let's say, theta, this is y, and now if we look at something like this, this is the curve of cosine theta. And now between, at this point here, this is pi over 2, and at this point right here, this is negative pi over 2. And then, so if we draw the inverse of it, which is like that, I mean the flip side of it, this is just going to be, well, 1 over cosine theta, which equals 2 secant theta. So if we select this as our range for our theta, so then in this case what we'll have is basically theta is less than equal to pi over 2, actually less than pi over 2, because as you can see it never actually touches it, and it's also greater than negative pi over 2. So we have that. So this is always positive. So in this case right here, it's always going to be positive, greater than 0. So this would just be equal to 2 secant theta. And this basically ensures that this is also a one-to-one function. And the reason, this has to be one-to-one is that we can't have multiple values of x that can equal something else. And I explained that more in my earlier videos on trig substitution, the introduction to it. So now that we have this part, we can begin solving our integral right here. So we have the integral of 1 over x squared times square root x squared plus 4 dx. This is equal to, and now when we apply all of this stuff to it, so this square root x squared plus 4, that equals to, well, 2 secant theta, and this x squared, that's just going to be, well, 2 squared times it by tan squared theta, and then this is all divided by right here 2 secant theta, and now the d theta, the dx, that's just equals to this right here, and that equals to 2 secant squared theta d theta. So now we just cancel the like terms, so there's the 2's cancel, the secant cancels with this, and now we're left with 1 over 4, this is 2 squared, integral of now secant theta tan squared theta d theta. And now what we could do is basically simplify this into terms of, instead of using secant and tan, simplify to sine theta and cosine theta terms, because they're easier, and especially when we use substitution further on. So what we could do is rewrite secant theta over tan squared theta as, well, secant is just 1 over cosine theta. Tan squared, that equals to sine squared theta over cosine squared theta. But since at the bottom we just flip it, and now what we can do is cancel here, we get cosine sine squared theta. So what we get over here is equals to 1 over 4 secant, actually not secant, this is cosine theta over sine squared theta d theta. So now that we have this, and what we could do now is we change a variable again, so let u equals to sine theta, and the reason for this is because du is equal to, that's just going to be basically cosine theta d theta. So we do this so we cancel the top part. So what we could do this now equals to 1 over 4, 1 over 4 times it by integral now of the top part, just going to be du, that's just this is the top part, it's du, and the bottom is a sine squared theta, that's just going to be, well, u squared. And now we could solve this integral. I'll just simplify this a bit further. This equals to u to the power negative 2 du, and now this equals to 1 over 4 times it by, and then now this integral of this, that's just going to be, well, u, then we add 1 here, u to the power of 1, and now we divide it by, well, negative 1 right here. And we all have to add c right here. So when we have this part, well, this is just negative 1, and that's just 1 over u, so this just equals to negative, take the negative out, and now just put the u underneath, so plus c. And where, well, the u, that's just equals to sine theta. So sine theta plus c. And now we have to, well, get back to the x variable. So to get back to x, put this like this, well, we use the original change of variable was x equals to 2 times tan theta, or rewrite this, that's just tan theta is equal to x over 2, and we know by definition tan theta is equal to, well, opposite over adjacent on a right angle triangle. So if we were to draw it like this, so that's a right angle triangle right there. Draw this better. So if this is the angle theta, the opposite is here, which is x. The adjacent is here, which is 2. And now using Pythagoras, the addition of these, this is just x squared plus 2 squared, which is 4. All square root is the hypotenuse. So now, what we have to do is get this part. Again, if we could simplify this even further, this is negative 1 over 4. That's just going to be, well, cosecant theta plus c. So cosecant theta is equal to, this is the reverse of the sign, so it's going to be hypotenuse over opposite, which equals 2 in this case, x squared plus 4, all divided by hypotenuse. Yeah, that's hypotenuse, opposite is just x. So that's what we have over there. So finally, if we put this all together, we get integral of basically dx over x squared square root x squared plus 4 equals 2. Change of variables, negative 4 times cosecant theta plus c, which equals to finally negative, now we have square root x squared plus 4 over 4x, now plus c. And there is our answer to this pretty extensive, this pretty complex example right here. Anyways, hopefully you learned from this video. That's all for today. Like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another Math Easy solution.